All right. So polar coordinates, rather than thinking about our standard kind of rectangular X and Y, we are instead reframing this in terms of R comma theta, where we can think of R loosely, very, very loosely, as like the distance from the center, just like our standard radius, and we can just think of theta as like the angle of rotation. Now we kind of understand pretty innately, maybe not that innately, maybe this is something that we've just been building up over the course of the last, I don't know, 18 years of our lives. But we understand pretty well the idea of what it means to have like a negative value of X or a negative value of Y, where negative X means we're to the left, positive X means we're to the right, negative Y means down, positive Y means up. In case of our R and theta, we've talked a little bit about what it means to have a positive value of theta and a negative value of theta. So just as a bit of a reminder, what does it mean for my angle to be positive? So what happens, what do I know when I'm looking at like pi over 4 rather than, let's say, negative pi over 4? What does this tell us? Yeah, so when we are positive in terms of our theta, then we are rotating counterclockwise. And when our theta is negative, we are rotating clockwise. Now, as far as our R is concerned, we've really only dealt with positive values of R because I've tried really hard to kind of keep this intuition that it's a radius, it's a distance. A negative radius doesn't really make all that much physical sense. Here, though, it is possible to have a negative value of R. It means something very, very specific. Normally, when we are starting with our kind of rotation, we start in the positive X direction. So when R is greater than 0, we have a start in the positive X direction. A negative value of R just does the reverse of that. Rather than starting in the positive X direction, a negative value of R will start us at the negative X direction. So you can kind of think of like the positive and negative and the actual size of the radius as kind of communicating two different pieces of information. The size is actually talking about the distance. So like the absolute value of R would tell you that distance. Whereas the positive or negative just tells you, do you start to the right of the center or do you start to the left of the center? Where? Yep, as is standard with what we've been doing. All right, so let's take a look at how we might actually go about plotting some of these. For example 1, we've been asked to plot 4 different points here. We're going to start with, we'll just kind of go through the list. Looking at A here, we've been asked to plot the point 3 comma pi over 4. Now, normally when we've been doing this unit circle stuff, we've been using kind of the outer edge of our circle as like the radius. Here, each of the kind of demarcations that we have going out is going to represent increasing that radius by 1. So for instance, that really small circle on the inside on the board there is like radius of 1, then 2, then 3, then so on. We see something similar here where this would be our radius 1, radius 3, radius 5, so on. So where am I starting with my point A here? What's being communicated to me? R is positive, so where am I starting relative to the center? To the right, so starting like here, we're out a distance of 3. And then how far am I going to be rotating, and what direction am I, really the direction here is what we care about. What direction am I going to be rotating? Counterclockwise by pi over 4. That will take us to right here. Whoa, what was that? That'll take us to right here. This will be A. Okay, looking at point B, what do we know? What does it tell us? Start with the R, then work our way to the theta. What is the R telling us? Right by 6, so starting here. And what direction am I going to be rotating? Clockwise by pi over 3, or by 60 degrees, will take me to this kind of terminal point here, which is our B. Okay. What does C tell me to do? Start to the left by 4. So 1, 2, 3, 4 here. So starting here. And then which direction am I rotating? Counterclockwise by pi over 2. That is going to take me to this point right here for C. Okay. One more for D. Where am I starting? To the left by 6. And how far am I, which direction am I rotating? Still rotating counterclockwise. And how far am I rotating counterclockwise? 2 pi over 3. Now, 2 pi over 3 is a quadrant 2 angle. So we're going to need to go like a full 90 degrees and then a little bit more, not quite a half rotation. So a full 90 degrees and then a little bit more. That should take us to right here. So something odd has happened here, something that we didn't ever really see with our rectangular coordinates or our Cartesian coordinates here. And that is that we have two different points, B and D, that are in fact not different points at all. They look different, right? One has a negative value of R, one has a positive value of R. The angles aren't the same at all. One's negative pi over 3, 2 pi over 3. Completely different looking points that are in fact referring to the exact same point. That shouldn't be that surprising, though. We've dealt with this a few times where kind of that final location, that resting position for angles can line up, can match. We haven't really seen it in this particular capacity, though, where we're like approaching from two opposite sides and we end up like coalescing like this. But what if we really called it before, when we have these angles that keep giving us this like similar end information? Yeah, those are like our coterminal angles, which we normally get when we are like over rotating or under rotating by a certain amount, right? Like adding 2 pi to my angle over and over and over again, that is going to give me my coterminal angles. Here, negative pi over 3 and 2 pi over 3 are not coterminal angles. You can confirm that if you would like to, but you can add or subtract 2 pi to both of these. You're never going to get them to line up. It just isn't going to work. But there's like this extra kind of foul play involved here with the positive 6 versus the negative 6, which is kind of why we're seeing this line up in spite of the fact that these are not coterminal angles. What this means for us is that there are an infinite number of ways to represent our polar coordinates, which is again not something that we see with the rectangular coordinates. With the rectangular coordinates, if you have different values of x, your point is going to be different. If you have different values of y, your point is going to be different. Here, it's not the case. You can have different values of r, you can have different values of theta, and the point can still line up, which is different. And it's just all about the kind of different ways that we are able to approach. So for example 2 asks us to find other representations of the point 5 pi over 4. It gives us constraints on this, and I'm aware there are typos there that'll be cleaned up by the time you guys have your notes. But we are going to not worry too much about those constraints. We're just going to kind of do this by hand, figure out what's going on with 5 pi over 4. So going out by 5, rotating by pi over 4, we are looking at this point here as 5 pi over 4. All right, so let's brainstorm here. What are other ways that I could arrive at this exact same final position? Yeah, we could just go the opposite direction. That is absolutely one. So we could start at the same point. We could rotate backwards, clockwise, until we reach that same position. That's fantastic. Now we have to figure out how far we've rotated. So our starting position here is positive x direction out by 5. So positive 5 for that value of r. We've almost done a full 2 pi rotation. We're a little bit short of that. What quadrant do we find angles that represent being a little bit short of a full 2 pi rotation around our circle? As a fourth quadrant, right? Notice here, we've rotated a full 90, we rotate a full 180, we rotate a full 270, and then we don't quite get all the way to the 360. We're sitting somewhere between a 270-degree rotation and a 360-degree rotation. That is going to put us in quadrant 4. What is the quadrant 4 angle that corresponds to pi over 4? Seven pi over 4, thank you. Oh, thank you. 7 pi over 4. But what do I notice about the direction that I rotated to get here? It was clockwise, so is it going to be positive 7 pi over 4 or negative 7 pi over 4? All right, so that's one way we could get there. What else could we do? Yeah, we could start on the opposite side. So maybe instead we start over here at -5, going out by 5 to the left. And then how could we get to, and actually I'll use the highlighter here so that we can actually keep track of it. So starting here, and then which direction could I rotate? We could go both ways. We'll look at both. So if we rotate, we'll start with counterclockwise here. We'll keep our theta positive here. If I'm rotating counterclockwise, then how long does it take? Well, it takes a half rotation and then a little bit extra. Notice we go a full 90, we go a full 180. We don't quite get to a full 270. So what quadrant does this angle live in? That's a quadrant 3 angle, so -5, and then the quadrant 3 angle that corresponds here, I get 5 pi over 4. Fantastic. And of course, we could also rotate in the other direction. There we go. Clockwise instead. How far do we have to rotate going clockwise? Well, again, we're starting in the negative x direction, so -5, and we rotate a little bit more than 90, not quite 180. That is going to be a quadrant 2 angle rotating clockwise, -3 pi over 4. Okay. One more way that I want to highlight, this is the way that we've really been doing it up until this point. If I also wanted to just start at 5 and 5 comma pi over 4 and keep the same kind of starting point and the same direction, what could I do to end up at the same point? Yeah, we could just find the coterminal angle here. So this would be like 5, and then 9 pi over 4 would represent going all the way around my circle once, and then an additional pi over 4 to get to exactly where we see right here. And we could, of course, add or subtract 2 pi to any of these angles, and they would take us again to this exact kind of terminal point that we see. Okay, so there are more than one way to arrive at any of the polar coordinate points that we get here. Thinking in terms of like what the positive and negative tell you in terms of polar coordinates, it's very, very tempting to be like, oh, the r is like the x value and the theta is like the y value because they line up completely, completely different. They are not, well, we're going to look at how they are related, but they are not that easily related here, where like having a negative r value doesn't automatically put us in quadrants like 2 or 3. Having a negative theta doesn't automatically put us in quadrants 3 or 4. It just messes around with the instructions that we're following. It changes the directions that we have to move, but it doesn't necessarily, we can't necessarily draw conclusions about where we end up. Questions here with our kind of basic setup with our polar coordinate system? Yeah, but it's more demonstrative than anything. More just highlighting the idea that, yeah, there are other ways that we can arrive at the same point. And the actual example 2 gives us like some constraints to work with. You'll notice if you actually do, when I hand out the packets, work through this example, that we find those solutions in what we have here. The answers to example 2 are exactly what we covered here. And then some, we cover, I think, one more. Yeah, Simran. Like the B and the D here? Just D? Okay, so where are we starting? Left by 6. So starting here. What direction are we rotating? Counterclockwise. So notice counterclockwise is going to be traveling this direction, whereas like clockwise would be the other. And then 2 pi over 3. How far is 2 pi over 3? Well, it's going to be more than a 90-degree rotation, but not quite a 180-degree rotation. So we go 90 degrees. We go a little bit more until we find that pi over 3 reference angle right there. And that's where we will terminate. Think of this as like pi over 2 plus pi over 3 would give us that 2 pi over 3. So we're traveling 90 degrees, and then we do an additional pi over 3. Or actually, that's not quite it. It's technically pi minus, but you get the idea. Yeah, exactly. It's the exact same distance that we would travel if we were starting on the other side. It's just because we're starting on the other side, we end up in quadrant 4 instead of quadrant 2. Yeah, exactly. I was just showing that you could arrive at this in a myriad of different ways. We already saw that with this particular example where we started for B, started here and rotated backwards and arrived at the exact same point. But we could also imagine starting to the right and then rotating all the way around. This would be like our standard way of doing it before arriving at this kind of final point. This is how we would normally do it, right? This would be the point 6 and 5 pi over 3. And that is probably the more kosher way of representing this, the more standard way with the positive r, the positive theta. Good questions. Other questions here? All right. So what we're going to work on next is moving between our coordinate systems. These are ultimately referring to the same points in the same space. These are just two different instructions on how to get there. One instruction book tells us move to the right or left, go up or down. One tells us slide out a certain distance and then start rotating. Either way, though, we're trying to get to the same position. There should be a function or a set of functions that will allow us to pretty seamlessly translate between that kind of rotational information and the standard x, y information. That's the direction we're going to focus on now. If we're given the rotational, how do we get back to the rectangular or the Cartesian? Now that being said, this idea of like taking in some kind of angle information and spitting out X information or Y information, that should be sounding horribly familiar to us all. What functions have we built that are designed to do that, that take in angle information and spit out X or Y information? Yeah, these are our trig functions, right? That's what we designed our trig functions to be able to do. This was our ability to take in one piece of unit circle information and translate it into another piece of unit circle information. So for instance, if we are looking at, and the geometric like circle definitions versus triangle definitions, these are of course all the same. This is theta, this is r, this is y, this is x. We've got this point, which we now know is either x comma y or r comma theta. Both ways of representing that are totally fine. And so what do I know about my trig functions? What kind of trig setups do I get from this? These are just the standard ones that we've been working with for a while now. Okay, yeah, what is cosine of theta? X over r. And other one being sine of theta, which is, yeah, just y over r. Now, if we're trying to take in r and theta and spit out x and y, it doesn't make sense to have r in our answer. We want r to be in kind of our input, what we're plugging in. And so what could I do here to isolate x and y? Yeah, multiply everything by r. I get that an equation that I said, I believe the first time we went over this, maybe like a month ago, that this was one that was going to keep showing up. The idea that x should be equal to r cosine of theta, and that y should be equal to r sine of theta. And so if I give you the r and the theta, it's very simply just a matter of plugging it into r cosine of theta to find the corresponding x value, plugging it into r sine of theta to find the corresponding y value. It is that simple. All right, let's try this with 3a. Now we could theoretically pretty easily actually approach 3a without employing these new equations that if you're going to get anything from this class tattooed onto you, it should probably be this. Actually, no, there are other things that are more important, but this one would be up there. That x is equal to r cosine of theta, that y is equal to r sine of theta. You're going to get very tired of hearing me say that by the end of this unit. So learn it now. We don't really need these to approach this one. This one's actually fairly straightforward. For instance, if we wanted to just think about the point 3 comma pi, what is this telling us to do? Where am I starting? Right by 3. And which direction am I rotating? Although here it doesn't really matter. Rotating counterclockwise by pi. So we stop here. What's this point in terms of x and y? What's the x coordinate of this point? -3. And the y coordinate? Yeah, just 0. So that one's pretty easy to just kind of graph and then approach. But let's confirm. Let's make sure that that is in fact what we are going to get when we try this. This is our r theta. We know that our x, y should be equal to r cosine of theta, comma, r sine of theta. In this case, we say r is 3 and theta is pi. What is cosine of pi? -1 times 3 is -3. And what is sine of pi? 0 times 3 is 0. Which, yeah, is exactly what we were expecting it to be, -3, 0. All right. Questions with our converting from polar to Cartesian with 3a here. All right, if we don't have any questions, take a stab at B and C here. Exact same idea. 5 minutes might be a little bit long on this one, but I'll say let's take 5 minutes to work through B and C. No, you do not. And then evaluate your assumptions. Looks good. Unit circle now for the final evaluation. we shouldn't need, you don't need to draw it. I was mostly doing that to demonstrate that, you know, this one it's not too bad. This one is going to be pretty hard to do just drawing. So I would try doing it algebra.
Please look at we don't. So then you're just evaluating what is cosine of pi over 6, sine of pi over 6, what is cosine of pi over 2, sine of pi over 2. This is good, and then just put it in the x, y final form, because that would be the actual form. That looks good. And then just evaluating the x, y, or the cosine. That looks good. Here, I think you got the cosine and sine left, so cosine of pi over 6, sine of pi over 6, root it to that. Perfect. Perfect. Looks great. Perfect. That's awesome. Yeah. So this is separate from a lot of values in Excel. R and theta are their own thing. This is a new rebranding, completely different way to think about it. So the theta is the second value. So that's the question. So notice here that our second values here, these thetas, they're all positive, so these will all be capital. R is the first value, which is going to determine whether we're starting to right, and how far in that direction. Does look perfect. All right, let's take a look here at what we have. In the case of B, for our R cosine theta, R sine theta, in this case, the R you plug in just as is. Just the -6, you don't need to adjust for anything because it's negative, don't need to make any kind of fancy arrangements. This is just -6 cosine of pi over 6 and -6 sine of pi over 6. What are cosine and sine of pi over 6? Cosine is √3/2, which I'm going to simplify to be -3√3 when multiplied by -6. And then sine of pi over 6 is ½ times -6, I get -3. Likewise for C, this is 2 cosine of pi over 2 and 2 sine of pi over 2. You don't have to do this all at once if it's easier for you to set up like an equation for x and equation for y. That's fine. I just don't find it to be particularly more difficult this way. What is cosine of pi over 2? 0. What is sine of pi over 2? 1. I get that this is the point. 2 times 0 is just 0. 2 times 1 is 2. All right. Questions here with
Example 3. Good thing to know, it's going to be coming up over and 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 over again. X is our cosine of theta. Y is our sine of theta. Over and over and over. Now the polar to rectangular direction is fairly straightforward, right? We just have our two equations here. We just take r, plug in r, take theta, plug in theta. The other direction, which is unfortunately the more difficult and also more useful direction, is just a little bit trickier. We actually can do something fairly similar where we try and construct two equations. I find that those two equations are kind of harder to deal with, particularly the equation for theta is a little bit trickier to deal with when we're thinking about them independently. Ultimately, that is going to be our strategy, though, is kind of comprising two equations. My advice would be to start with r. So if we're thinking about our triangle here, thinking about what we have here, what is my equation for r? What can I say about r? Assuming I'm given x and y, right? This is, again, taking x, y information, translating it into r and theta information. What can I say about r in terms of x and y? Say again? Yes, but that requires us to know theta as well. Yeah, this is just Pythagorean theorem information. So this would be like the square root of x squared plus y squared. And if we have first found r and now just need to find theta, well, now we can use our equations that we have set up, where cosine of theta must be x over r, and sine of theta must be y over r. We can use those equations to either deduce what r must be, or we'll show this kind of direct comparison method that we have for figuring out the value of r. So first we're going to find r. That way we can set up our equation for theta. It'll make finding theta easier. If I didn't want to do this, if I wanted to just have those two equations and I wanted to change the order, we could do this in terms of tangent, right? Tangent of theta equals y over x. That doesn't involve r at all. So we don't really need to, we wouldn't need to start by finding r. But I feel like not our as in like this class, but just like our as in like myself included, ability to translate from tangent information to corresponding unit circle information is harder than if this is in terms of sine and cosine, which we're a lot more practiced with. So I like kind of leaving this in terms of sine and cosine. Not that it's necessary, just that it's my preferred way. So taking a look at 4a here, we are given this time rectangular coordinates. So 0, -4 is an x value of 0 and a y value of -4. We want to translate this into some kind of r comma theta. We'll start with the r value here. R being equal to the square root of 0 squared plus -4 squared.
which should just give us an R value of 4. 0 squared is 0, negative 4 squared is positive 16, square root of positive 16 is positive 4. Technically, yes, we could do like plus or minus here. You could use negative 4 as your value for R. There's nothing mathematically wrong with that. But just to keep things simple, I will always have my R be positive, and I will always have my theta be positive when I'm doing this. From here, we can set up our equations for finding theta. In particular, that cosine of theta must be 0 over 4. That's our x over r. And that sine of theta must be negative 4 over 4, or negative 1. What are the two thetas that would have an x value of 0, where cosine of that theta would be 0? Very good. This is either pi over 2 or 3 pi over 2. That's got to be one of these two. We could use what I might describe as like meta inferences here, where we look at the point that we are trying to translate and say, okay, does this make more sense as pi over 2? Does it make more sense as 3 pi over 2? For instance, noticing that we have this negative y value here, the only way we could start to the right and rotate counterclockwise to get to a negative y value by going past pi over 2, so 3 pi over 2 probably makes sense. This would normally be like looking at what quadrant we're living in. So in particular, 0 and negative 4 lives between quadrants 3 and 4. But we could, for B and C, for instance, say, okay, we're looking for a quadrant 2 angle or a quadrant 4 angle or a quadrant 3 angle, whatever, and then use that information. That would also be fine. The other way we can do this is we can actually just find the thetas that work for not only this first equation, but also the second equation, and whichever ones overlap, that will be our final answer. So for instance, if sine of theta is equal to negative 1, what is, in this case, the only theta such that sine of that theta is negative 1? That's going to be 3 pi over 2. And so notice 3 pi over 2 here shows up twice, and so is going to be our actual theta that we will use here. And so our point, r comma theta, the point for 3 pi over 2. All right. Questions with 4A? All right, take a stab at B and C.
Here? Yeah. Is our R just It's good. It's good. Which is good because we know units have more information about those too. We don't know about the denominator of Yeah, so what's the so -1 squared is going to be 1, right? Remember that if you plug this in your calculator, you need to make sure you have parentheses here so that actually it's the so that actually squares. And then the square root of 3 squared is going to be what happens when you square a square root? Yeah. So the square root of 3 squared is just going to become 3. And then adding those, taking the square root of what you get there. Yep. Looks good. Okay. So these two thetas look good. Now we could also use so what you're doing here is where you would like find these two and then like compare and take that on line. That's it. We could also just look here and say what quadrants does this one live in? And so we could take that. And either way it's perfectly fine. One kind of requires I think the difficulty in quotes comes from like slightly different places. One requires more unit circle information because you got to know the sine and the cosine as well. The other one requires you to look at the point and be able to translate that into quadrant information, but I don't think that those are perfect. But I think that's fair. Sure. Yes. I'm not sure. So I just figure out like what quadrants. So looking at cosine, when is cosine going to be negative? There's 2 quadrants. Okay, and so what are the thetas that we see where cosine is 1/2 in quadrants 2 and 3? 2 pi over 3 and 4 pi over 3. Okay. So those would be kind of our 2 candidates. Now we could then do the same thing with sine when it's positive. What are the 2 angles, and then look at the overlap. That would be totally fine. You could also look at the point. Is the overlap just going to be like whenever they're in the same quadrant? Yeah, look at where where we could have negative cosine and positive sine. Yep.
It's the same for both. It's the same for both of them.
Yeah, so because where is sine positive? There, 1 and 2. And so the only place on the unit circle where we get negative cosine and positive sine is.
wait,
Yes, we
plan
could
was like
rationalize
2
that
months
if you wanted to
on
make it a little bit
And none of
more.
us combined anything.
Yeah, for sure. Yeah.
Is this one, is that one five miles?
You'd want to put it in the form of r comma theta, but that's your.
Okay.
Yeah, that's,
And then my R.
r is that value that you found for you.
And she's asking for guidance. No, what? Gummies. It says look through the ingredients. Yeah, 'cause gelatin's there's it's really delicious, literally powdered sugar and corn syrup.
All right, let's take a look here. What is the R value that we found for B? R value is 2. Very good. And so the equations that we get, I get that cosine of theta is -1/2, and that sine of theta is √3/2. We could, again, kind of similar to what we did for the first one, find all the thetas, look for the overlap, that's fine. But we could also look at this point. Where does this point live? -1√3, where is that going to live? Yeah, that's just a quadrant 2 point. And so we're looking for a quadrant 2 angle to go alongside our quadrant 2 point. Cosine of theta equals -1/2. What are the two values of theta for which that is true? Yep. And other one would be 4π/3. But which one is the quadrant 2 angle? 2π/3. And so we absolutely could be done there. But for the sake of showing, if we wanted to compare what we get from sine of theta, we would get either that theta was π/3 or 2π/3, where notice here that 2π/3 is the only theta that is shared between the two. And for C, what is the value of R that we get? 4√2, very good. And so the equations that I get that cosine of theta should be 4/4√2, which simplifies to 1/√2. I get that sine of theta is -4/4√2, which simplifies to -1/√2, which look very, very different than a starting with trig. What are these equivalent to, though? Yeah, this is the same as √2/2 and -√2/2. What quadrant does -4 live in? Fourth quadrant. And so what is the fourth quadrant angle that is going to be giving us √2/2? Theta is going to be 7π/4. Of course, our final answer should be the point itself, not just the individual pieces. And so for B, our answer would look something like R, theta. And for C, our answer would look something like R, theta. Questions with converting our polar coordinates or our rectangular coordinates? All right. Trying to think. Yes, I do have a thing. So we've got about 10 minutes left. You guys do have a Pearson over 6.1 and 6.2. It's a little bit on the longer end in terms of just like the sheer number of questions, but a lot of those questions are like graph the point or like can like find the equivalent forms, things like that. So it shouldn't be a huge amount of time. It's a lot of like small questions instead of like some longer
larger questions. You guys have the rest of this time in order to work on that. Of course, if you have any questions, you are more than welcome to ask. And so yeah, just take this time to work through what you got.